Hello everyone, my name is Zijun. I come from Shanghai Jiao University, EPCC lab. Today I will give a talk to introduce help rather than recycle, elevating code startup in serverless computing through inter-function container sharing. In the first section, I will briefly introduce what serverless and fast are, and what are the advantages and limitations of using serverless model. First, what is serverless? According to Berkeley's view, serverless equals fast plus fast. Developers upload their codes as functions to the fast system. User triggers a function through events like HTTP requests. The fast system allocates computing resources and interacts with the backend services to execute functions. In the traditional ICE-based serving model, computing and memory resources are pre-allocated and have no clear relationship with the number of concurrent service requests. Even if there is no request for a period of time, resources are still occupied. On the other hand, serverless computing can charge per request without paying for waiting, which can achieve more efficient resource utilization. Using serverless model, we can achieve many benefits, like on-demand container launching, fine-grained resource scaling, offloaded management, and flexible scheduling. However, these features also bring diverse challenges. For example, the event-driven feature means if a function is invoked for the first time or there is no alive or warm containers for it, the serverless system has to start a new container to encapsulate its function runtime, initialize the software environment, load application-specific code, and run the function. All these steps make up a code startup and may even take several seconds. The code startup significantly increases queries end-to-end latency. The long latency problem worsens when the function invocation is short. In this talk, we focus on the challenges of code startups, and the high density and high concurrency challenges are discussed in our another talk about round D. Now we know that the code startup is an important issue. Does it really compromise the quality of service in the production? According to the Azure's report of production service traits, the function invocation follow a Pareto distribution. When we monitor the code startup frequency from the node perspective, code startup invocations are less than 1%, because most invocations come from popular applications. However, these popular applications account for only 20%. It means that if we monitor the code startup frequency from the view of multi-tenants, about 80% of all applications may frequently experience code startups. To get a good experience with the serverless model for most applications, we should optimize the problem from the perspective of all applications. So in this section, we will introduce how to elevate the code startups and analyze the efficiency of the current methods. The pre-warm-based methods create containers and runtime in advance. One method of which is pre-warming customized containers for each function that includes all its required software packages. It shows good and stable performance and can adjust the pool size for each pre-warm pool. However, it brings heavy memory consumption. Azure study focused on this exclusive pre-warm model to train a prediction model for resource-friendly pool size management. However, for most infrequent functions, the history execution trace may not expose enough data to train an accurate model. Another method of pre-warming containers is only installing common packages, and all functions share the template container pool. This method is more memory space efficient, but generating customized containers in the specialization phase for a function from the pre-warmed containers suffers from packages download and installing latency overhead. The overhead may introduce from several aspects and the performance becomes unpredictable. First, all functions share the same pre-warm pool. The pre-warm pool is more likely breakdown with high concurrency code startup. Take ECO and cart as examples. Their functions are invoked concurrently or in short intervals to satisfy complex business logic, such as serverless workflows. This phenomenon attributes to the inappropriate pool size of the pre-warm container pool. So does it mean if we increase the pool size, the code startups can be elevated proportionally? We find that even though we set a larger pool size, the code startups elevated converge to a stable value, because many functions require runtime environment with conflict packages or package versions. In this case, the serverless system has to retry with code startup and cannot be elevated by larger pre-warm pool size. In addition, even though a function can get a pre-warmed container that without poor contention and an image conflict, its specialization of loading additional packages may introduce more overhead than directly code startup. As shown, the code container startup takes about 500 milliseconds. The pre-warm startup takes 15 milliseconds in the best case, but takes more than 1,500 milliseconds in the worst case. For example, the benchmark DDNS. This is because functions in DDNS requires to load and store many additional packages in the pre-warmed containers, and the package loading is time-consuming. When using template-based pre-warm pool, there are trade-offs that are inevitable. As reported from Azure study, most of the invocations are from a small part of the functions. A pre-warmed container can only cache a small number of packages for the low memory overhead. Caching packages for frequently invoked functions improves the system efficiency, but results in poor user experience, and vice versa. In summary, if we use exclusive pre-warm method, we need to adjust pool size dynamically. The possible solution is to profile and predict for each function at runtime. However, the overhead of building predicting model for each function is high, and infrequent functions may not have enough data to train. So, our insight is that the current container pre-warm method is not efficient due to several inevitable trade-offs. It is beneficial to elevate code startups without trapping in the same dilemmas. We therefore propose to elevate code startups without relying on pre-warming containers. The key idea is leveraging the warm but idle containers of some functions to elevate the code startups. A function invocation that requires code startup may share an idle warm container from other functions. Our solution is called Pagurus. In nature, Pagurus is a kind of helmet crab that used abandoned sea shells as mobile homes. As a crab grows, it needs to move into a bigger one. However, empty shells are few and far between, so they usually arrange themselves in order queue. In such a way, they could reuse others' shell and move into it quickly. If we see these unsuitable shells as idle containers, can we make a cold startup function, like a crab, to reuse other shells? The proposed scheme is effective only when there are idle warm containers in some functions, when the invocation tends to suffer from the cold container startup. In principle, only underutilized warm containers that are active due to the keep alive strategy can be used by other functions. Otherwise, always stealing a warm container directly may result in the cold container startup of the victim function. Fortunately, serverless computing systems usually adopt a keep alive strategy, for example 15 minutes, to reduce the cold startup. The kept alive containers are idle before they are recycled. The widely existing dyno load pattern also makes containers over-provisioned at the high load. These containers will become idle when the load drops as well. One may be concerned about the security and privacy of the idle container for reusing. To this end, we propose Zygote container to replace an idle container. It does not include any data or code of the owner function, which means it can serve as a safe checkpoint for sharing. In general, the common packages required by all functions are installed as a shared domain in the Zygote container. These content are mounted anonymously into the Zygote, thus ensuring that others cannot identify a function. Each function that may use the Zygote container is given a privileged domain and is only allowed to access its corresponding packages directly. The privileged domain and the privileged control are provided by Linux operating system and different non-root users. So how does Pagurus work with Zygote containers? It has 4 main steps. Pagurus will identify the idle containers in each function pool at runtime. Once identified, Pagurus will build Zygote image and then replace an idle container with a Zygote. If a to-be-held function is going to cold startup, Pagurus will schedule a Zygote container and fork a helper container for this function to reuse. In the system, each function may have Zygote containers. So how does Pagurus arrange Zygote containers for appropriate forking? We introduce a similarity-featured weighted random sampling algorithm. It selects to-be-helped functions based on the package similarity between functions and the frequency of function cold startups. SFWRS policy reduces the number of packages to be installed, thus minimizing the memory needed and the overhead of creating Zygote containers. With above designs, Pagurus can elevate the cold startup by reproposing a warm but idle container from another function. In this section, we will introduce our evaluation process. We use 10 best practice applications with the most GitHub stars from Amazon AWS samples as benchmarks and the Azure trace to evaluate Pagurus. Fast Profiler and the Serverless Bench show similar results. As observed from replaying Azure's trace, Pagurus reduced the number of cold startups by 84.6%. About 73.4% of all functions experience cold startup less than once in a day with Pagurus. Meanwhile, 90% of the functions experience code startups less than 5 times daily with Pagurus. The code startup latency is reduced from hundreds of milliseconds to 16 milliseconds if alleviated. For end-to-end latencies, popular functions have similar 94% tail latency with OpenWhisk and Pagurus. This is because the slowest 94% tail latencies of these functions still experience warm startup, as these functions are frequently invoked. For the middle popularity and the low popularity functions, their 95% tail latencies are the latency of the function invocation that suffers from the code container startup with OpenWhisk. So Pagurus indeed brings lower end-to-end tail latencies. Finally, we give our conclusion on Pagurus. In summary, Pagurus proposed to reusing idle containers to elevate code startups. So it introduced Zygote containers that contain the shared domain and privileged domain to provide security and privacy. When scheduling Zygote containers, we use a similarity-filtered weighted random sampling algorithm, which can improve the inter-function container sharing efficiency. Another related track presentation called RunD introduces how to construct container runtime in serverless computing to enable high density and high concurrency startup. You can also contact us by email with any questions. Thanks for listening.